Very good morning, everyone. Myself, Balamurugan. I am very happy to present a topic named Analog Communication Methods in Communication Engineering. First, we will see the syllabus for this particular subject. Here, what are the core subjectives? The main purpose of reading this subject is we have to understand analog communication techniques. The next thing is we have to learn the pulse modulation techniques, and we have to understand the digital communication techniques. We understand the multi-user radio communication, and then finally we learn to how to use the communication technologies. So after reading and understanding all these kind of techniques which are used for communication, the next thing is how we apply in our real world problems. Those are all listed here as course outcomes. In the first unit, we will see the analog communication methods. So in this one, first we give introduction to communication systems, and next we will see what is modulation and what is the need of modulation, what are the types of modulation. Next we will see the theory of amplitude modulation. So up to this particular topic we will see in this particular hour. Okay, let us go to the presentation straight away. So here we will see, the first unit title is analog modulation. Here some introduction is given. So in the introduction, we cannot have we cannot transport the information signal as it is. If we want to transmit the information from one place to another place, a transmitter, that is between the transmitter and the receiver, we have to use some transmission medium, right? So before transmitting these signals, we have to make these information signals more suitable for transmission, right? So how we make the information signal suitable for transmission is we use one particular process that we call that as modulation. The process of modulation is nothing but we try to incorporate two signals together. One signal is called information signal and the other signal is called carrier signal. And then after we combine these two signals together, we can transmit the information signal over the carrier signal. That is called modulation. And what is demodulation? Once a signal is transmitted over the medium, we will receive the modulated signal at the receiver. So if we want to we want to receive the original information, we have to use the process called demodulation. So it is the reverse process where the received signal are transformed back to the original form. Let us see the block diagram for communication system. Let us see the diagram for communication system. Okay. As we said, the low frequency signal must be made low frequency signal must be made suitable for transmission. So here the information is nothing but the low frequency information, right? When we transfer this information to the transmission medium, this will be amplified once, and the frequency of this information signal is combined with the high frequency carrier wave with the help of modulator, right? And we use the frequency up converter here to increase the frequency of the information, and the output of the modulator is given to the power amplifier, and the output of the modulator is called modulated wave. Why we use power amplifier here means we have to increase the amplitude, we have to increase the level of the modulated wave. That's why we use power amplifier here, and the output of the power amplifier is transmitted through the transmission medium. So initially we had the low frequency signal which is combined with the high frequency carrier wave in the modulator, and the output of the modulator is given to the power amplifier where we increase the power, and then finally the increased amplitude signal with of high frequency is transmitted over some medium like air, and then at the this is called a receiver. Here we use the amplifier again, right, where we will have the modulated wave, right. Here we have used modulator and frequency up converter. Here we use demodulator and frequency down converter, right. We use the frequency down converter. Here we also high free we are here also we use high frequency oscillator. Here also we use high frequency local oscillator to generate the high frequency carrier wave, right. So finally the demodulator output is the exact information what we transmit initially here. That is what is the input is given to the modulator finally can be obtained as output from the demodulator. That's it. So next we will see what is the necessity of modulation, right. It is really difficult to radiate a signal which has low frequency and low amplitude, right? So we need modulation. We need modulation because of these reasons, right? The first one is reduction in antenna height. If you use modulation, the antenna used will be a smaller one, and long distance communication. It can be used for long distance communication. Easy of radiation. Easy to design amplifier circuit and antennas at high frequency if we use the modulation. Otherwise, the design of amplifiers and then the antennas used in the communication process will be a difficult one. The next thing is multiplexing. Multiplexing means different signals can be transmitted, right, over the same channel without interference. Multiplexing means simply combining simply transmitting more than one channel, more than one signal in a channel. That is called multiplexing. Multiplexing means many inputs and single output. That is the concept of multiplexer. So here we combine different signals together, right? And then we use to transmit the signals in the same transmission medium without any interference. The next thing is improve the quality of reception, and then the last one is avoid mixing of signal, right? Next, we will see the classification of modulation. Majorly, two types of modulations are there. One is called analog modulation, and other is called digital modulation. Analog modulation can be otherwise called as continuous modulation, whereas the digital modulation is otherwise called discrete modulation. So we have first we will see the analog modulation types. The analog modulation is further classified into two types. One is called continuous modulation, and the other one is called pulse analog modulation. Again, the continuous modulation is divided into two categories. One is called amplitude modulation and other is called angle modulation. Further, angle modulation is divided into two things. One is called frequency and the other is called phase modulation. So up to this, we will see in unit number 1, and the other techniques we deal with unit 2, unit 3 like that. Whereas the second type of analog modulation is called pulse analog modulation. In this one, we will have PAM, PPM, PWM. That is called. Okay, we will see them when we see them in detail. And then the digital modulation is again further classified into two things: pulse digital modulation and shift keying methods. The pulse digital modulation is divided into PCM, DM, ADM, DPCM like that. And then shift keying methods are classified into ASK, FSK, PSK, QAM. ASK is called amplitude shift keying, and then F is called frequency shift keying. Here PCM is called pulse code modulation. D is called delta modulation. This is called adaptive delta modulation. This is called digital pulse code modulation. Okay, further here is called pulse amplitude modulation, pulse position modulation, pulse width modulation. These kind of techniques are here as pulse analog modulation. Okay, here we will see some general terms. What is analog signal and what is digital signal? Analog signal is called in analog signal we will have the amplitude changes with respect to time continuously. Example is called a sine wave, whereas in the digital signal, we will not have the changes in amplitude continuously with respect to time. We will have the amplitude in certain time periods only. There's those time periods are called discrete time periods. So these signals are also called as discrete signals. So these signals will have values like zeros and ones only. They call those as binary signals. Next thing we call that as frequency. The formula for frequency is F equal to 1 divided by T. If we consider the variation of a signal over a period of time, for example, look at this diagram. So for one complete time period, that is one positive cycle and one negative cycle, together the time period is called capital T. So the inverse time period is called frequency. So frequency is a number of now times a periodic motion occurs in a given time period, right? Okay, the unit of frequency is hertz. Okay, next we will see wavelength. The formula to calculate wavelength is wavelength equal to velocity divided by frequency. Symbol wise, wavelength is lambda, velocity is c, and frequency is f. So the formula is lambda equal to c divided by f. C is nothing but velocity of the light. Okay, the value for that one is 3 into 10 power 8 meters per second, which is constant, which will never change. Only the two things will change, the wavelength and the frequency. Okay, next we see one signal that is called sinusoidal signal. Two types of signals are represented here. One is V of t, that is called voltage, and other one is called I of t, that we call as current. V of t can be written as V into sine 2 pi ft plus theta, whereas I of t equal to I sine 2 pi ft plus theta, where V of t and then I of t or time varying voltage and current value of sine wave. V is the peak value of the voltage and f is the frequency. Theta is the phase shift. The unit for phase shift is radian and I is nothing but peak value of current. The unit is ampere and for voltage the unit is volts. And then 2 pi f is called angular frequency. Here the unit for angular velocity is radians per second. Okay, here some two types of representation of the signals are presented. One is the time domain representation and other one is called frequency domain representation. Time domain representation is similar to this thing where we have the variation of amplitude with respect to time. Next we will see the frequency domain representation. In frequency domain representation, we try to represent the signal variation with respect to frequency, right? So here we call in y-axis amplitude is there, whereas in the x-axis we have the frequency, right? Next we will see what is bandwidth. Bandwidth is defined as a range of frequency over which information signal is transmitted. Let us see. Let us consider one signal here, right, which has two frequency. One is the upper frequency and the other is the lower frequency. And bandwidth is simply the difference between these two frequency. That is called f2 minus f1. 4k minus 500. 4k means 4000 minus 500, so it will be 3500 hertz, right? Here in y-axis we represent the signal magnitude, that is signal magnitude in decibel, signal value in decibel, whereas on the x-axis we have the frequency. Next, the signals can be classified according to the frequency, right? That they call that as a frequency spectrum. It will start with 3 kilohertz and it will end with 300 gigahertz. So we start with very low frequency, and after that low frequency signal, after that medium frequency, after that high frequency, and then very high frequency, ultra high frequency, and the last two things are called SHS and EHF. SHF and EHF. Okay, and then application of these signals wherever we use communication, right? Like cellular, telephone, microwave, satellite radio signal, radio communication, marine. These are all application of communication system. Okay, fine. Next, we will see the two types of signal. One is called continuous signal, and other is called a discrete signal. This is also called a digital signal. As we said, the analog signal or continuous signal is continuous in nature, in which the amplitude changes continuously with respect to time. So you can see from here, whereas in the digital signal, we will have the uh, value at some specified time periods, in not all the time periods as we have in the analog signal, right? Okay, fine. Next, we will see the first type of modulation that we call that as amplitude modulation. The definition is, what is amplitude modulation? The definition for amplitude modulation is a process by which the amplitude of the carrier signal is varied in accordance with the instantaneous value of the modulating signal. Okay, if we replace the amplitude changes of carrier signal with respect to the modulating signal as phase, that will go for phase modulation. If we replace the amplitude variation of carrier signal with respect to modulating signal with frequency, that we call that as frequency modulation. And the other two parameters, we go for the amplitude modulation, the other two parameters that are phase and frequency, those things will remain constant. Okay, here we will see AM modulator. One block is given. The input to the AM modulators are two signals. One is the information signal and the other is the carrier signal. Both of them are given to the modulator and the output will be a combination of these two signals, right? That signal we call that as modulator signal. Okay, fine. Now let us see what is information signal, message signal or modulating signal. Okay, first we will see what is signal. Signal, as we said, which will have the useful information that has to be transmitted, which has low frequency, right? Next is the carrier input. Carrier input is a high frequency signal, right? Which will have a constant amplitude. And the modulated output, which is the output of the modulator, that we call that as modulated signal in the envelope. We call that as envelope is AM envelope. AM envelope is nothing but this particular thing in which the carrier signal is loaded like this. Okay. Now we will see the mathematical representation of the AM signal. So we will consider all the three signals together here. One is the unmodulated signal and other is the modulated signal and the third one is the carrier signal. First we see the unmodulated carrier wave, right? The representation of unmodulated carrier signal is nothing but this one. Vc of t is equal to Ec into sine 2 pi fc into t. 2 pi fc is nothing but the angular frequency and Ec is the peak carrier amplitude, right? And then Fc is the carrier frequency. Okay, that completes the representation for unmodulated carrier signal. And the second signal is, which is nothing but the modulating signal. Modulating signal can be represented as Vm of t equal to Em into sine 2 pi Fm into t. Here Vm of t is the time varying waveform, time varying amplitude or time varying waveform of the modulating signal, and the next thing is the Em. Em is the peak value of the modulating signal, and 2 pi Fm is nothing but the angular frequency of modulation. If we take Fm, that is nothing but the modulating signal frequency, and Fc is nothing but the carrier frequency. And we know the unit also of frequency, just nothing but hertz. That is given in bracket here. Okay, and the last signal, just nothing but the modulated wave, just nothing but VAM of t, right? VAM of t, which is nothing but the output of the AM modulator, right? An AM waveform is produced when a single frequency modulating signal act as a high frequency carrier signal. The output of the modulator, which is nothing but a high frequency signal, that we have to know. Okay, let us see the three signals together. This is nothing but unmodulated signal. This is the carrier signal, right? And the third one, which is nothing but we call that as AM envelope, the upper part and the lower part of this particular diagram, in which the information is presented. Information is presented. Okay, here two types of bands that will be available. One we call that as the lower sideband here, and the other we call that as the upper sideband. That is nothing but here. Here we will have two amplitudes of this particular wave that we call that as V max and V minimum. V max is equal to EC plus EM, right? V minimum equal to EC minus EM. We know what is EC and then what is EM, right? Yeah. Okay, since this particular AM modulated wave contains two sidebands, that is the lower sideband and other one is the upper sideband, we call it as DSB. That is nothing but double side band envelope. AM envelope. Okay. Okay, fine. Let us see the representation of the modulated wave, that is VAM of t equal to EAM into sine 2 pi fc into t, right? Where EAM is nothing but the addition of two things, EC plus EM sine 2 pi FM into t, right? Okay. If we substitute the EM value here, then VAM of t can be written as EC plus EM sine 2 pi FM into t into sine 2 pi FC into t. Okay, so this is the final representation for the modulated EAM signal. Next, we see one important parameter that we say that as modulation index. It is also known as modulation coefficient, right? Otherwise, we call that as percentage modulation. So modulation index is the ratio of two things, EM divided by EC. That's it. That is the peak. That is the peak value of modulating signal divided by peak value of carrier signal, which is nothing but modulation index. It is always expressed in terms of percentage, so we call that as percentage modulation. So according to the modulation index value, we can define the types of modulation. There are three types of modulation that are available according to the value of modulation index. First, we call that as critical modulation. The value for that modulation index is 100%. 100%. If EM is equal to EC, right, then this value is possible. 100% of modulation index is possible. So if that is the case, we call that modulation technique as critical modulation. And the second thing is under modulation. Under modulation means EM will be less than EC. So if that is the case, then the modulation value will always less than 1. So we call that as under modulation. Under modulation means it is less than 1. And the third type is nothing but over modulation, in which EM is greater than EC. If that is the case, we will have MS greater than 1. So we can call that as over modulation. So three types of modulations that are available. One we call that as critical modulation, and the other we call that as under modulation, and the last one is the over modulation. Let us see the AM frequency spectrum and the bandwidth. Okay, so here we have two bandwidth for AM modulated wave. One is we call it as lower sideband and the other is called upper sideband. Lower sideband frequency is given as FC minus FM and the upper sideband frequency is given as FC plus FM. Okay. Here we see the spectrum, frequency spectrum. Here y-axis we can take the amplitude and in the x-axis we take the frequency. And at the center we have the carrier frequency that is called as FC. If we add FM to this FC, we will have FC plus FM. So from FC to FC plus FM, we will have the upper side band, and the frequency that are presented here are called as upper sideband frequency. Whereas if we add minus FC with FM, we call that particular band as lower sideband, and the frequencies that are present here we are called as lower side frequency. Okay. Next thing is the bandwidth. How we can calculate the bandwidth is nothing but upper sideband frequency minus lower sideband frequency. Upper sideband frequency is Fc plus F max, whereas the lower sideband frequency is minus Fc plus F max. So Fc will get cancelled, and the bandwidth for AM modulation is 2F max. 2FM max. Okay. So here other two types of formulas are given, right? That is called power in amplitude modulated wave, in AM wave, right? Here PT is given as PC into 1 plus m squared by 2. M is the modulation index, PC is the carrier power, and then PT is the total power. And then this is the power spectrum of the AM wave. Okay, whereas the AM current can be given as IT equal to IC into root of 1 plus m squared by 2. IT is the total current, and then IC is the carrier current. And then the transmission efficiency. Transmission efficiency. What is transmission efficiency? What is the total power that is present in the sideband divided by total power of the AM wave into 100. So if you put the power values here, the efficiency formula will be written as m squared divided by 2 plus m squared into 100. Why? Because efficiency is always expressed in terms of percentage, right? Here you see if you put m equal to 1, right, what will happen? If you put m equal to 1, what will happen? 1 divided by 3 into 100. So the percentage of efficiency will be 33.33. Right, so this particular percentage is used to transmit the signal. Remaining power is wasted in the carrier and the sideband signal. So only 33% is used. 33% of power is used to transmit the signal, and the remaining, like 66 percentage, 66.7, like that, the total power is wasted in the carrier and then the sideband signals. Okay, fine. Next, we will see the first type of AM modulators. In case of AM modulators, there are two types of modulators that are available. One we call that as double sideband modulator, and the other is called as single sideband modulator. Okay, when the AM modulating circuit is considered, we will have two types. One is the square law or non-linear modulator, and the other one we call that as linear modulator or high level modulator. Okay. And then this one here, low level AM modulator is explained here, and what is the advantage. And the second type, square law modulator, is explained here, which is nothing but non-linear modulator. And then the demodulator, then the demodulation of double sideband is given here. Here, double sideband SC signal, which is nothing but S of t, is given to this particular product modulator, right? And the other input to this modulator, which is nothing but local oscillator, which is used to generate the carrier signal, which is represented as EC into cos omega C into t. So the product modulator has two inputs. One is the double sideband SC means suppressed carrier signal, and the other is the local carrier signal. And the output will be the product of these two signals that we call that as V of t, right? And after this input is given to the low pass filter, and then finally the required output V of t is obtained here. This is the original information what we transmitted in the DSP modulator. Here, this particular detector is called as coherent detector. The word coherent meaning is synchronization. That is, the transmitter and the receiver are in synchronization together. That's why they call that as coherent detection. Here, the double sideband signal is multiplied with the carrier signal, which is generated by the local oscillator. And The output of the modulator is called VFT, is passed through the low pass filter, and then this low pass filter is used to get the information what we want, right? Only the filtered output we will have as output from the DSPD modulator, right? Okay, let us stop here. From the next lecture, we will see the single sideband suppressed modulator and then double sideband modulator. And those modulators, we will see it in the next class. So now let us go for an overview what we have seen so far. First, we have seen some introduction to communication system, how the information signals are transmitted, right, by a process called modulation, and what should be done for the information signal before transmission. And what is demodulation? Demodulation is the reverse process of modulation, which is needed to get back the information signal again. So this is the block diagram of the communication system. You see one transmitter and you see one receiver, and the components which are used in the transmitter and the components that are used in the receiver. And the next thing is, what is the necessity or need for modulation, and what is the classification of modulation process. Majorly two methods, analog and then digital modulation, and then further analog modulation are classified like this, and then further digital modulation techniques are classified like this. And then what are the general terms that are used? What is analog signal and what is digital signal? What is frequency and what is wavelength? And then what is sinusoidal signal? Most preferably we use the signal as sinusoidal signals. So what is V of t and what is I of t, and what are the terms that are present in the representation of sinusoidal signal are explained here. And then the two types of representations. One we call it as time domain representation, and the other we call it as frequency domain representation. And how we can calculate the bandwidth, and according to the frequency, how the signals are classified. So this will tell that particular thing. And these are all some types of communication systems. And here we have seen what is a signal. After that, what is the difference between the continuous signal and the discrete signal. With the help of diagram, they are explained here. And then first, we see what is amplitude modulation, right? And what are the parameters that are kept constant during the amplitude modulation process. And then this is the block diagram for AM modulation. Here we have explained three signals: what is information, what is carrier, and what is modulated signal. And then the representation for each type of signal. Here unmodulated carrier signal is represented. Here the modulating signal is represented. And then finally the modulated wave VAM of t is also represented. So three types of representation. Here we see the three different types of diagram: unmodulated signal, carrier signal, and the modulated signal. Okay, this is a representation for AM wave. And then what is modulation index, and what is percentage modulation, and what is the importance of modulation index, and the different types of modulation according to the value of modulation index. First type is called critical. When M is equal to 1, EC is equal to EM, and the other one is called under modulation. EM is less than EC and M is less than 1. And the other thing is called over modulation, where EM greater than EC and M is greater than 1. Okay, next we represented the frequency spectrum of AM wave here, which has lower sideband and upper sideband, and now we can calculate the bandwidth for that particular thing. And then the phasor representation is explained here, and then the power, how to calculate the total power of AM wave, and then the current, how we can calculate the total current in AM wave, and finally the transmission efficiency. Okay, for typical value m equal to 1, what is the percentage of efficiency in AM modulation that is explained. And then the next thing is the DSB modulators. Two more types of modulators are here, right? Modulators, as I said, we will see it in the next hour. Next thing we have seen the DSB demodulator. DSB demodulator, right? DSB demodulator. The block diagram is given, and how these components will work that are explained here. So thank you for everybody for listening to me with patience. In the next class, we will see the other types of modulators in AM modulation and the demodulators. Thank you. See you in the next hour.